elementary row operation is some basic things that we can do to a matrix to kind of transform it. It's still an equivalent matrix, but we've changed it a little bit. Think about like when we use elimination, when we do the process of elimination, how we multiply one of the rows by something, one of the equations by something. It doesn't change the system, it just changes how it's written. So essentially that's what we're doing. Elementary row operations, you are allowed to interchange two rows, so just have two rows switch places. You can multiply a row by a non-zero constant, so if you want to multiply the whole row by 2, you're allowed to do that. And the third one is you can add a multiple of a row to another row. Okay, think like elimination here, kind of like that process. So sometimes these are just easier to see. On number 3, we want to find the row operation that's being performed. Okay, so what happened from the original matrix to the new one to change it? So take a look at row 1, 1, 0, 2, 1, 0, 2. That did not change. Okay, second row, 3, 1, 7, 2, 0, 1, 1. That obviously did change, so we'll come back to that. Third row, 2, negative 6, 14, 2, negative 6, 14. That didn't change. So the only change happened from here to here. Now we need to figure out what it is. Obviously no two rows were interchanged, otherwise we would have noticed that. This was not multiplied by a non-zero constant. There's no way to multiply, there's no non-zero number that we can take 3 times something and get 0. So what happened is number 3, we added a multiple of a row to another row. So somehow we got 0 right here. So that means somehow we took this 3 and we added a negative 3 to it. So I'm guessing what happened is this row got multiplied by a negative 3, and then row 1 and row 2 got added together. Okay, because if negative 3 times 1 is negative 3, and then add that here, you get 0. Negative 3 times 0 is 0. Add that here, you get 1. Negative 3 times 2 is negative 6. Add that here, and you get 1. So that is what happened. So now we need to write down what it is. We took negative 3 times row 1, and we added it to row 2. And that was the elementary row operation that happened here. We will be doing a lot more with that in a bit. Another key term that you probably talked about in Algebra 2 is row echelon form. So there's some criteria for being in row echelon form. Any rows that are entirely zeros are at the bottom of the matrix. All other rows have 1 as their first coefficient. And the leading coefficient 1 in each row is further to the left than the leading one in the lower row. Okay? Furthermore, that's just row echelon form. Reduced row echelon form is when every column that has a leading 1 has 0 in every position above and below it. So we're going to take a look at these examples and find out, is it in row echelon form, and if so, is it in reduced row echelon form? Okay, so this first one. Let's see, we don't have any, what were our criteria again? Row 0's at the bottom, leading coefficient of 1, further to the left. Okay, we don't have any rows of 0's in this first one. Are all of our leading coefficients 1? Well, no, not that. So this is not in row echelon form. Let's take a look at the next one. We don't have any rows of 0's to worry about. I do see that all of our leading coefficients are 1, and all of the leading coefficients, the highest one, it's further to the left than any of the ones below it. So this is good. It is a yes. This is in row echelon form. Okay, now is it in reduced row echelon form? The additional criteria is that every column that has a leading coefficient 1 has 0's in every position above and below it. Now here's the problem. See this 1? Above it is this 3, and to be in reduced row echelon form, that would need to be a 0. So this is a no. And our last one is going to be a yes for both of those. I'll let you look through the criteria and figure out why.